From Dr. J. Boy, are you quantum gravity because I'm relatively attracted to you. I have no idea what you're referring to or what you're talking about, but thanks. Hi, I'm Brian Greene, physicist, professor, author, and I am here today to answer your questions from the internet. This is Quantum Physics Support. At Paylene Misery. Do people actually understand quantum physics, or do we all just pretend that we do? We understand the core ideas, but they're very different from the things that we would think should happen in the universe based on our common experience. So we have to reorient our thinking to align with the discoveries of quantum physics, and that's not easy, but it is something that those of us who immerse ourselves in these ideas are able to do. So yeah, we do understand a lot about quantum physics. Next question from @Stuxman. Has some grizzled professor, like me, poking a pencil through a folded sheet of paper to explain wormholes ever made anyone go, aha? Still seems like an incomprehensible magic to me. Take 2 points on a piece of paper. I can draw a line connecting them, and you can see that that line is kind of big. So imagine this is in space. Maybe this is the Andromeda galaxy, and this is our Milky Way galaxy. The fabric of space can be manipulated. It can warp so that these two locations that were very far apart are now very close together. So if I stick a pencil through, you now see that the orange between the two locations, that would be a wormhole. We don't know if wormholes are real. They emerge from the mathematics of general relativity, but if they do exist, in principle, they could provide a shortcut from one location to another. From Doozy. If I ran into a wall over and over again, would quantum tunneling allow me to eventually pass through the wall? And if yes, can we calculate or estimate how many times I would need to run into the wall to pass through? Yes, exactly. That is what would happen. Now look, we don't do quantum mechanical experiments with macroscopic beings like a human body, but we do a version of you running into a wall with a particle like an electron or a neutron or a proton that we fire at a barrier over and over and over again. A small fraction of the time, we do find it passes through a barrier that classical physics says it can't. If you scale this up, yeah, in principle, a many particle system like your body could undertake the same experiment. You'd have to hit this barrier an enormous number of times, exponentially large in the age of our current universe. That's just how ridiculously tiny the probability that you will pass through the barrier is. Asus Remus, is our universe the only universe? You would think that our universe is the only universe because it's the only one that we can observe with powerful telescopes. But there's mathematics suggesting that the Big Bang may not have been a one-time event. There may be many bangs giving rise to many expanding universes that all populate a grand multiverse. I like to think of it as a giant bubble bath where the individual bubbles are universes like our own, but the grand picture contains many of these bubbles, many of these universes. Some people, when they encounter this idea, they say, you're talking nonsense. You're no longer talking science. They have a point. This is an important criticism, but let me just note 2 things. Number 1, in principle, this may be a testable idea. If 2 of these bubble universes were to collide, there is mathematics suggesting that the collision could leave an imprint on what's known as the microwave background radiation. We've not yet seen it at all, but in principle, if we did, this would be circumstantial evidence in favor of this idea of multiple universes. The second point I would make is a theoretical statement. We theorists use mathematics to try to understand reality. For instance, the Big Bang idea has been tested by detailed observations of space. It has confirmed the predictions, which is wonderful. But if the math then says there should be other universes, we are willing to go where the math takes us because we have confirmed the parts of the mathematics available to our observations. Do we know that that's the case? We don't. but we are willing to consider it because of the fact that the mathematics suggests that this really may be true. At Junesy's Girl, do we have any updates on time travel? Cause please take me back. If you wanted to see what was happening on planet Earth 1 million years from now, Einstein himself laid out a blueprint for how, in principle, you could do that. You travel out into space near the speed of light. Say you go 6 months, you turn around, you come back for 6 months. You will be 1 year older, of course, but because your motion was near the speed of light, your clock was ticking slow compared to clocks on planet Earth. So when you step out of that spaceship, it won't be 1 year into the future on planet Earth, and maybe 2 years, or 5 years, or 10 years, or 100,000 years, all dependent on how close to the speed of light your ship was able to travel. But many of us are more interested in traveling back in time, and that's the one where we just don't know. There are proposals that people have put forward using exotic things like wormholes or interesting kinds of motions around cosmic strings, but whether any of those ideas really work, we don't have an answer. And so we suspect that travel to the past is not possible, but as of today, nobody has definitively ruled it out. At Calypsy asks, physics was up. Why is teleportation not possible? It's not possible for macroscopic objects like you and me, but physicists who work on teleportation routinely teleport individual particles from one location to another. You set up two entangled particles that in some sense act as one even though they're far apart. You bring in whatever you want to teleport and it commingles with one of the entangled particles, and through the magic of entanglement, its features get imprinted on the distant particle. This person can manipulate that particle and extract an exact copy of the original. And in that way, effectively, you have teleported a particle from one location to another. At Sign-On Ghost Riley, what is reality made of actually? Like, what is this universe? Way back in the early days, people thought it was earth, air, fire, and water as the basic ingredients of everything. In the early years of the 20th century, people got on board with the idea that matter is made of fundamental constituents made of atoms. And as we examine atoms with ever greater precision, we realize that there are other particles that make up atoms. You've got electrons that are in orbital clouds around a nucleus that typically has neutrons and protons. And the neutrons and protons themselves, we know, are made of yet smaller particles known as quarks, arranged in correct configurations, and electrons. They are the bulk of matter as we know it. My guess is at some point we will talk about atoms making up the fabric of space itself. I think there will be fundamental constituents of space and fundamental constituents of time. What those ingredients actually are, we are still struggling to figure out, but my guess is that that is where our understanding will lead us. All right, next question is from Sparsh Mather. When does quantum mechanics get weird? Well, it gets weird almost from the get-go, right? Quantum mechanics tells us that the world can be in a blended mixture of different mutually incompatible states of being. It tells us that distant objects can be weirdly connected through something known as quantum entanglement. It's weird from the beginning, and yet it works. Isaac Newton described the world in terms of billiard balls bouncing around according to ideas and laws that he was able to intuit. For reasons that we do not understand, the microworld doesn't behave that way. Instead, it plays by these different rules called quantum physics. And here's what's remarkable. The rules that Isaac Newton wrote down, we can extract them from quantum physics. So perhaps the real way of talking about the world is it's quantum mechanical through and through, and quantum mechanics suppresses the weird stuff in the microworld as things get larger and larger, making the world appear to play by the rules of Isaac Newton. But fundamentally, everything is quantum mechanical through and through. All right, a user at Quora asks, if nothing can escape a black hole, how do they eventually die out? Stephen Hawking determined way back in roughly 1974 that black holes may not be as black as the mathematics of Einstein's general relativity suggests. Particles, in a sense, can leak out of a black hole quantum mechanically, and as particles slowly radiate from a large black hole, the black hole gets smaller and smaller, which means the intensity of the radiation becomes bigger and bigger until at the very end there's a gigantic burst of radiation, which in essence is the death throes of a black hole. A black hole with the mass of the sun will take about 10 to the 68 years to radiate enough matter that the black hole will shrink down to its final state of nothingness. But what happens then? Nobody knows. From Explain Like I'm 5 subreddit, if an electron can be two places at the same time, how do we know those are not two different electrons? We fire a single electron into an experimental context in which the results that we find can only be explained if en route to the detector, the electron took two different pathways from start to finish. Since we only put one electron into the experiment and we only get one electron out from the experiment, when we find in the intermediate stage that the electron is in some sense at two places at the same time, it's only one electron that's doing that, not two. From @DrinkMoreGravy. I just learned about the block universe theory, and now I'm having a major existential crisis. It's funny that you're having an existential crisis. To me, the block universe idea is very comforting from an existential standpoint. So what's the basic idea? The idea is rather than thinking of the past as being gone and the future is yet to be, we imagine that all of time is out there within this block that has all of time and all of space. From that standpoint, we always exist because the block itself containing all events, it never changes. So in that sense, nothing ever dies. Everything that exists at a given moment always occupies that position in the block. From @Miniapure, is string theory dead? Spend too much time scrolling on the internet, you might get the impression that string theory is dead, but the fact of the matter is, string theory has been making enormous strides in understanding black holes, in understanding the nature of space and time. String theory has not been able to make any predictions that we can test in the laboratory, but please bear in mind, physics is more than that. Physics is trying to understand a coherent description of the external world. We don't have such a coherent description. Gravity and quantum mechanics are at loggerheads, but string theory is the best developed at putting the two pillars of physics together into one consistent framework. On that front, string theory is absolutely an enormously important development in the history of ideas. From Devon Skenadore, if everything has a beginning, then when did time begin? And if time had a start, what was here before that beginning? There's nobody on our planet who does know the answer to that question. We do have ideas. Let me just throw out a couple of them to you right now. It could be that there is a beginning to time. An analogy helps grasp what that would mean. You know, if you're walking on planet Earth and you want to go further north, you can pass by someone and say, hey, can you point me in the direction of further north? They point northward. You keep on heading, you pass somebody else. Point me in the direction of north. They point you toward the North Pole. When you get to the North Pole, and you say to someone there, how do I go further north? They'd look at you kind of funny and say, the concept of further north than the North Pole is meaningless. The North Pole is where north begins. Similarly, it could be the case that you can imagine going back 100 years, 1,000 years, 1 billion years. When you get to the Big Bang, it could be that the concept of going further back in time is as meaningless as going further north than the North Pole. It could be that time itself simply began with the Big Bang itself. There are other ideas that people have developed where there is a prehistory to the Big Bang. In fact, there are some theories that envision that our Big Bang is simply one expansion of space event that is one of many times that the universe has undergone this kind of rapid outward swelling. which means there could be other Big Bangs, other universes populating a grand multiverse. From Jerswar at the Explain Like I'm 5 subreddit, what is the big deal with quantum computers? In quantum mechanics, a particle can be in multiple places at the same time. A quantum computer leverages that multiplicity to carry out multiple calculations, in essence, in parallel, which gives you a multiplier effect on how fast the computer can, in principle, get to an answer. But there's a second part of quantum computation, which is, it's not enough that it does all these calculations in parallel. How do you find the answer among that multiplicity that you are looking for? And so for a certain class of questions, a quantum computer can give rise to an exponential speedup. But for other questions, the exponential speedup that works for other problems won't be applicable. And so my suspicion is that quantum computers will be a very niche-oriented kind of device that are really good at a certain category of questions, like simulating quantum systems or factoring numbers into their prime factors, but unlikely to be an all-purpose machine that sits on your desk or on your lap and does the kinds of things that ordinary computers do, the kinds of things that we are familiar with. From @Kirosak, what the is quantum entanglement? In the everyday world, if two things are far apart, we know that they can act independently of one another. But in the quantum world, two things can be far apart, and yet they are locked together from a behavioral standpoint, even though they are far apart in space. Imagine you've got a particle whose spin, we call it, is pointing up or down, is in a mixture of both of those. And you can have two of these particles. If they are quantum entangled, a measurement on one of these particles coaxes a single definite reality. The other particle, if they're quantum entangled, will also snap out of the fuzzy haze and acquire a single definite reality. Even though they're far apart, quantum entanglement bridges the gap between them and allows their behaviors to be tightly choreographed in a way that we're still struggling to fully understand. But the laboratory experiments are clear. What you do here quantum mechanically can have an impact over there if the two objects are quantum entangled. Next question is from the Change My View subreddit. Schrödinger's cat seems like a dumb concept. Maybe you don't fully understand the idea of Schrödinger's cat then, because it's anything but a dumb concept. Back in the 1930s, when quantum mechanics was being developed, you might have tried to argue that the weirdness of quantum mechanics can be sequestered into the microscopic world, and we simply don't need to think about it or worry about it in the macroscopic world. Schrödinger's cat was introduced by Schrödinger to lay that thinking to rest. And he basically said, look, if you have an electron, a little particle, that's in a 50-50 mixture of being here and being there, you might say, well, okay, I'm willing to accept a particle in some mixture of being two places at the same time because it's in the microscopic world and I don't need to worry about it in the macro world. And Schrödinger says, no, we can amplify the weirdness of the micro world into the macro world. All we need to do is set up a little gadget which has poison that will be released into this box if the electron's on the right-hand side, but it won't be released into the box if the electron's on the left-hand side. And then if we put a cat in the box, the poison is in a 50-50 mixture of being released and not being released, which means the cat must be in a 50-50 mixture of being dead and alive. Quantum physics, he was saying, its weirdness necessarily has a trajectory whereby it can infect the everyday reality that we experience. At Resonance Enter 1, does observation create reality? There are physical systems where if there is no observation, there is no measurement, the system evolves and behaves one way. But if there is interaction and involvement, that interaction does change how the system behaves. A single photon, if it sufficiently impinges on a particle like an electron, that photon can coax a definite reality to emerge. One of the deep questions in quantum mechanics that we have not yet fully understood is, why is it that an observation or a measurement can have such a radical impact on a quantum mechanical system. Somehow intervention, environmental influence, observation or measurement is important to this transition, but exactly how this happens, this is something that we are still struggling to understand. El Kabong, why do atoms not run out of energy? We've known since the 1800s that as electrons accelerate, they radiate away energy. And if they radiate away energy, that electron should spiral into the nucleus and crash. So why doesn't that happen? The answer, according to quantum mechanics, is that there is a lowest energy state that's available to a system like an atom, such that there isn't any way in the world for the atom to achieve a lower energy configuration. And so quantum mechanics itself places a limit on how close the electron can get to the nucleus of the atom. We can actually calculate that lowest energy state, and then we can compare it to the energy states of atoms. Energy can be quantized. It can come in chunks that can't be subdivided, that can't be diminished. From the Manuko subreddit, at the smallest level, we have quantum physics. At the normal level, we have relativity. Is there another set of laws for super big things? You're right, for the very small, we have quantum mechanics, but I would say for the super big, we have general relativity. That's Einstein's theory of gravity, and gravity becomes ever more important when things are ever larger, for stars and black holes. We are the in-between, the very small and the super big, and we are necessarily a blend. And so there are things in the world that we are familiar with where quantum mechanics rears itself and flexes its muscles more strongly. There are other things that we encounter that have general relativity flexing its muscles, but we haven't found that there's a new set of laws that we have to introduce to understand the in-between. Instead, our challenge is to put general relativity and quantum mechanics, so the calculations that we human beings in the middle actually do, we want those calculations to make sense and to make sensible predictions. And that is a blending that we have been trying to do for, 80 years. From @IgnoreThatDoor, why does anything exist? In the beginning, there was totally nothing, so how did something come from nothing? We don't know why there is something rather than nothing. All we physicists can do is we assume that there was something, energy, matter, a configuration that can give rise to the Big Bang, and then from that point forward, we analyze what happens to that something, how that something manifests as particles that then come together to yield stars, galaxies, and so on and so forth. But if you push further back and ask, why is there anything at all? Nobody really has an answer yet for that. There is one idea that I can just throw out. A state of absolute nothingness may be unstable. A state of absolute nothingness may quantum mechanically fall apart into a something and an anti-something. Do we know that that's the case? We don't, but at least it's an interesting idea for how you could start with nothing and yield a something. @TrollOnPatrol, what happens after the universe dies? I wrote a whole book on it. In fact, it's the bottom book in this little stack under here, Until the End of Time. We don't know for sure, but one dominant possibility is that in the very far future, the universe will continue its spatial expansion. As it expands ever more widely, material objects will continue to disintegrate, stars will disintegrate, planets will disintegrate, even black holes disintegrate into a bath of particles. And so that suggests that in the very far future, the universe will be nothing but a bath of particles wafting through an ever larger, ever quieter, ever colder cosmos. Long before any of these structures existed in the early universe, it was just particles. Those particles come together for a brief period of time, giving rise to the stars and galaxies and planets, and on this planet, people as well. And then in the far future, it all disperses once again. So everything that we know about, everything we care about, everything that matters to us may just be a momentary aggregate of particles that comes together for a brief period, then falls apart, and then for effectively an eternity, there's nothing but particles wafting through the void. All right, that's all for today. Thanks for joining us. Hope you learned a little bit about quantum physics and the universe. This is Quantum Physics Support.